Okay, Physics 11H, let's look at a couple different examples for how we use the electric field. One of my favorite simulations on the FET.Colorado.edu doesn't really work anymore. It was called Electric Field Hockey. I think we could still run it down in Mr. Kalilum's room. I believe they're on his it's on his computers. But they haven't made a new version of it yet, and it used to be based on Java. And what that was there was a goal, and alumni. If any alumni watch this video, they'll remember this lab. They loved it. We used to do like a March Madness, not a March Madness, but like a impromptu tournament, so to speak. And what it was is you'd have a puck, and I want to say it was positively charged. It was like a ball or a puck, and you'd have to make it in the goal. And so imagine this is like a little positive charge. So if you want to make it in the goal, what you can do is you can place negative and positive charges around. So this applies a force to the puck flies into the goal. All right, so the electric field, due to this here, would repel, or sorry, positive, I'd have to make it, would repel the positive puck, right? Because the electric field of a point charge, as we saw in the simulation, goes out like this, right? So it's going to apply a force to this puck and push it that way. Now, what made this fun was a few of the higher levels, and you can try getting it to run. It's called Electric Field Hockey on fet.colorado.edu. It's still there. It's just you have to install Java, which is not a thing anymore on most computers due to security issues and such. So what would happen is they put a barrier in here, right? Then you have to make the puck, this little positively charged puck, make it around the barrier and into the goal. And the way you did that was you put a little positive puck here to give it an initial push, and then you could put a positive charge up here, so when it moved towards this, it would get repelled away, and then kids would put a few negative charges behind the goal to then attract the positive puck into the goal. And then it got crazy. There was another one like this, where you had to make it go between the two barriers and into the goal, which, believe it or not, you could get it done with only like 3 charges. That was like the pro level. And then there was one that was crazy impossible. It was like multiple turns, and kids would get it, but there was only one way to do that, for making a tunnel. But anyhow, so what electric fields do, again, let's just review. E equals force over charge, or the force on a charge is equal to QE. And this is the electric force. So if you have some random particle hanging out there of some charge, it's going to experience a force that is proportional to the amount of electric field that is present. All right? And if you remember, obviously, this is all a little bit of review here, so this is good. When you apply a force to something, it'll accelerate or change velocity. All right? So if something starts at rest and you apply a force to it, it'll start to accelerate. So the electric field we draw is like this these external arrows, E. All right, so we're going to just kind of look at a couple questions about that, a couple examples using work, energy concepts, because we're going to have to learn about electric potential energy, and stuff like that. And then we're going to do our final unit of circuits, a conceptual unit on circuits, basically. I think our final unit. I'm not exactly sure yet. But anyhow, I'm not going to exactly do this homework page. I'm going to assign 4 and 5 for homework tonight to be submitted tomorrow. But I'm going to do some examples that are similar. So one very similar to number 4, let's do first of all. It's not actually number 4, but let's say a 10 microcoulomb charge is placed in a positive 10 microcoulomb charge placed in a 30,000 Newton per Coulomb electric field. And it's accelerated over a distance of 0.40 meters. So what does that look like? I place a charge in a field. So I'm going to draw arrows to represent the field. All right. And I release this charge As soon as I release it, it starts from rest, so V initial equals 0 meters per second. It starts from rest, and it's gonna accelerate, right? So this particle is gonna get faster because it's gonna have a force acting on it. All right. There's our little Q. Has this arrow is actually representing its velocity. You know, it starts off little and it's going to get bigger because of this force pushing it to the right. It's a positive charge, so the force goes in the same direction as the field. All right, and we're going to let it accelerate over a distance of 0.40 meters. All right, and what I'm asking you is determine the work done on the object. So work is change in kinetic energy. So there's a few ways I could do this, or it's force times distance. This is the way we'll do it. And then you'll see in a second, once we know the object's mass, we will figure out how fast it's moving at the end of this distance of acceleration. All right. So let's go ahead and calculate this out. I'm gonna erase this to give myself a little room. I wrote a little large over here on the left. So the amount of work done here on the particle is going to be the amount of force times distance. The force is QE, and the distance, we'll leave it D. So Q is 10 microcoulombs, 10 to the negative 6 coulombs. E is 30,000 newtons per coulomb over a distance of 0.40 meters. All right, so I can put all this in here. 10 to the negative 6 times 30,000 times 0.4 gives us a total amount of work of 0.12 joules of work. Doesn't seem like much, but I didn't give you the mass of the particle, right? Let's say the mass of this particle is 1 gram. 1 gram, which is 1 times 10 to the negative 3rd kilograms. I gave you units of micrograms, so that would be 10 to the negative 9th kilograms. 10 to the negative 9th kilograms. I'm sorry for that again that I did that, but it's what I did. So if I want to figure out its final velocity now, I have to take that work and set it equal to change in kinetic energy. So this is no different than anything we've done so far. Or I could do F net equals MA, which actually might end up being easier, right? A is change in velocity, you know, so there's different ways to do this. I can show you both ways. So let's go ahead. Let's bank this work. Let's write it down here. Work equals 0.12 joules. See if that's useful. So 0.12 joules equals the change in kinetic energy equals kinetic energy final minus kinetic energy initial. Since it starts at rest, the initial kinetic energy is 0. So 0.12 joules equals kinetic energy final, 1/2 mv squared, 1 times 10 to the negative 3rd kilograms times v squared. We're looking for v squared. So v equals the square root of 2 times 0.12 divided by 1 times 10 to the negative 3rd. Now, let's see what we get here. Second square root of 2 times 0.12 divided by 1 times 10 to the negative 3rd equals about 15.5, or we'll say 15 meters per second. All right, that's your final velocity. I could have done F net equals MA. All right, so I could have done F net equals MA, and I could have done QE equals MA. A is delta V over T. No, I couldn't have done that because I didn't have the time. Duh. Anyhow, work equals change in kinetic energy. Important to know that. So work equals force times distance equals change in kinetic energy. The force on a charged particle is the charge times the electric field strength. So that's how you do number 4. Number 5 is just, again, it says this is introducing the concept of voltage, and I'll show you this in a second. So how many joules of energy does a 4 microcoulomb charge particle pick up if it's accelerated through a 1000 Newton per Coulomb electric field over a distance of 1.0 meters? That's just, again, work equals change in energy equals force times distance equals Q times E times D. All right. So the E times D here for part A and B, that's not going to change, right? Because the only thing you're changing is the charge from part A to B. So E times D is it's a 10,000 newtons per coulomb over a distance of 1.0 meters. And look at that. Look at the units you get. You get 10,000 Newton meters per coulomb, or 10,000 joules per coulomb, right? Newton meter is also known as a joule. All right, the field times the distance that the field's acting for. Turns out that's going to be 10,000 joules per coulomb. It turns out that a joule per coulomb is what we call a volt, which you probably have heard of. It's the amount of energy available in a field per coulomb of charge that you place in the field. And we'll come back to that and talk about that more later on. I basically did part C for you. So wrap those 2 questions up for homework. We'll see you guys later. We'll talk more about voltage in the next worksheet. Be good.